Okay, this is going to be the part 2 video for chapter 14, 15 in AP Statistics, talking about the foundational probability rules. And today we're going to talk about the rules for or and we'll talk about the special case for and. We'll save the special case for or. Well, maybe we'll do the special case for or. Maybe I'll put that in this video too. Probably will, actually. All right, so we talked about just general terminology and the difference between a simple probability and a conditional probability in the first part. And the idea is that with a simple probability, you're considering the entire sample space. And with a conditional probability, you're imposing a condition that restricts you to the conditional sample space. All right. So now we're going to talk about what's called compound events. That means that we have more than one event that we're combining, like a probability of one event or another event happening, or a probability of one event and another event happening. And we'll talk about the or case first. Let's say we have a deck of cards, and I know not everybody's familiar with cards. This is a standard deck of cards without jokers. There's 52 cards divided into 4 suits: clubs, diamonds, hearts, spades. And then the clubs and spades are black, the hearts and diamonds are red. There's 1 through 10, where 1 is represented by an ace with A, and then there are 3 face cards: jacks, queens, and kings. All right, if we draw 1 card from a standard deck of 52 cards, what's the probability that that card is a club or a diamond? Okay, well, we could analyze that this way. We could say every one of these cards is equally likely to be drawn. Right, so I have to have some way to indicate this. We'll talk about this. Well, let's talk about it right now. We're just going to list all the cards that are either a club or a diamond. And so I've got all the clubs here, and I've got all the diamonds here, right? And then if they're all equally likely, so there's 52 cards, that means that the conditional sample, or the sample space, is the entire deck of cards. That's why the bottom here is 52. And then out of that, we would just count up all of these outcomes here that meet the event, 26. So that would be half the deck, right? I want to introduce a symbol here, and it's this U. Okay, that U stands for union. And this is our official set way to show or. So in this class, whenever I refer to or, I'm going to use this U symbol. So start getting used to that symbol meaning or. So this is finding the probability of getting a single card to be a club or a diamond. And it's half, because that's half the deck. All right. We could actually separate those two things, though. Club is by itself an event, and diamond is an event, right? And we can find the probability of club and diamond separately. We know that the probability of finding a club would be, out of the 52, 13 of the cards here are clubs, so that's 1/4 of the deck. And 13 of the 52 cards are diamonds, that's 1/4 of the deck, right? So it's kind of interesting that if this probability of a club was 1/4 and this probability of a club is 1/4, if you add those up, you get the same 1/2, right? So it does seem to be true that if I have a probability of one thing or another thing, we should just be adding up the probabilities of the individual things, right? In fact, a lot of people memorize this, that or equals add, and that's a good thing to memorize. Whenever we have probability of one thing or another thing, we add the probabilities. Think about why that's true, because if you have one way for something to happen, and then you have additional ways that you can also get in the club, like let's say we want to find the probability that you're in the science club or the math club. Well, that means there's more ways for that to happen. So the probability should go up if there's more ways for that to happen. So it makes sense that it would be add. And in fact, it is add, but there's a catch. Okay, so we'll explore the catch here. Okay. What if I did this? We draw 1 card from a deck of 52 cards. What's the probability that the card is a diamond or it's a 5? Okay. Well, we could first do that just by listing the whole sample space out, the entire 52 deck of cards, right? Here's the sample space, 52, right? And there's 52 cards. And then I could say, okay, let's include all the ones that are either a diamond or they're a 5. So here's all the diamonds here. Here's all the 5s. So if I carefully count all those, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 cards out of 52. And that's the correct probability of getting either a diamond or a 5. And by counting it that way, I didn't double count this 5 in the middle here. So the correct probability is 16 out of 52. Okay. So let's try our thing that we said before, which is maybe we could calculate the probability of a diamond, getting a diamond, and then a probability of getting a 5 and add those, because OR is add, right? So the probability of getting a diamond is, it's 13 out of the 52 cards. And the probability of getting a 5 is 4 out of the 52 cards. But if you add 13 out of 52 and 4 out of 52, you get 17 out of 52, which is not correct because we know the answer should be 16 out of 52. So what happened here? Well, what happened is we double counted this 5 by including it in both counts. Right? The problem there was there's an overlap between the two. Okay. So if I want to adjust this so it's correct, I could still use the idea that OR equals add, okay? But I have to adjust for this kind of catch, right? You could take the probability of having a diamond, which is 13 out of the 52 cards, right? You could add on the 4 out of 52 probability of having a 5, but then you have to subtract off this overlap one so it doesn't get counted twice. Subtract it once, which is 1 out of 52. And what is this overlap? Well, this is the probability that a card is a diamond and a 5, right? So we have to subtract off the overlap case, which means we subtract the and case. So if I had 13 out of 52 plus 4 out of 52, I would get 17 out of 52. But when I subtract the overlap and case, I get back to the correct answer of 16 out of 52. All right. So that wasn't a problem in our first example with diamonds and clubs. If you look at the Venn diagrams for the two, right? Well, the one we just did here was out of all of the 52 cards here, right? Some of them are diamonds, some of them are 5s, but we have an overlap. There's a card in the middle here that's both a diamond and a 5, right? When we did the one before, we said, what's the probability of having a diamond or a club? But none of the diamonds are clubs because all the clubs are red and all the diamonds are black and all the diamonds are red. There's no overlap. So we didn't run into this problem because there was no overlap to get counted twice. All right. So we're going to use this to build a formula. I do want you to memorize that OR equals addition. Okay. We add probabilities if we have one thing or another, but we have to remember this too. We have to subtract off any overlap. So here's the true probability formula for OR cases. The probability of A or B, if A is some event and B is an event, like diamonds or clubs or diamonds and 5s or something like that, is the probability of event A plus the probability of event B, but minus the probability that A and B occur at the same time. And using the symbols, we're going to use this symbol for OR, the union symbol, and we'll use this upside down U to mean and. Okay, the U stands for union, and the upside down U stands for intersection. Okay, so start getting used to those symbols. I'm going to use them early in the class, so we get used to seeing them. All right, so that's the true OR formula. OR is addition, but subtract off the AND case to subtract off any overlap. To visualize this, we could look at kind of two Venn diagrams. This is what I picture in my mind when you give me an OR case, right? Generally, events do overlap, and that means that the probability of A or B is the probability of A plus the probability of B, but we have to subtract the probability of A and B, okay? But there's a special case that it can occur. Sometimes we don't have overlap. And if that's true, then this probability of A and B would be 0. There's no chance of that happening. And so we get a simpler version of the OR formula that the probability of A or B is simply the addition. Okay. So what makes this the special case is the probability of A and B is 0. If it's not true, then we have to use the general probability formula, right? And there's a special name for this special case. This special case is called when the two events are mutually exclusive. That's the term for the special case where there's no overlap. There's a second name for it too, which is disjoint events. And the reason that it's called that is because in this case where we have an overlap here, the probability that this occurs is called the joint probability. You can think of it kind of as a joint, like your arm and your top of your arm and your bottom of your arm connect at your elbow. So that's the joint, right? So this is the joint probability. And if the joint probability is 0, right, then that means these are disjoint events, right? So disjoint and mutually exclusive are two ways to refer to the same thing. It means we have the special case where there's no overlap. Okay. So we can define a test for disjoint or mutually exclusive events. Two events are disjoint or mutually exclusive if there's no overlap, which just means the probability of A and B occurring together is 0. There's no way they can both happen at the same time. Okay, so given this, you have enough information at this point to try problems 6A and B, and 7A and B, and 8 and 9. So I would like you to pause the video and give those things a try, and then unpause and I'll work these. Okay, let's take a look at each of these. So problem 6, this says, if a single six-sided die is rolled, find the probability of getting a number greater than 3 or an odd number. Okay, so there's a couple ways we could do that. In fact, let me bring this to another piece, another screen, so I can just work on that problem. Okay, I'm going to show you two ways you can do this. Okay, one way, and often in probability there's more than one way to do it. As long as you pick a valid way, it'll work. All right, one way you could do, and I would always recommend doing this, is list the sample space somehow, right? So the sample space for this is a single die, so I can get these outcomes, 1 through 6. Okay, for part A, we could find the probability that the number is greater than 3 or an odd number. So you could just take the sample space listing, 1, 2, 3, 4, 5, 6, and just count up, just use these things to include all the things that would be in there. Here's the sample space. You could think of this as making an event space. Let's say I'm only going to include the numbers from here that are greater than 3 or odd, right? So I'll look at each one number and see, does it meet this criteria? 1, is it greater than 3 or odd? Yes, it's an odd number, so it gets included. 2, is it greater than 3 or odd? No, so I don't include it. 3, is it greater than 3 or odd? Yes, I'll include it because it's an odd number. 4, is it greater than 3 or odd? Yes, because it's greater than 3. And 5 and 6 will be included because they're greater than 3. And since all these are equally likely, the probability of having something be greater than 3 or odd would be 5 cases out of the 6 cases, right? So it's 5 out of 6. That's one way to do it. You can basically take the sample space and then go back and highlight all the cases that meet the criteria. All of these do. So out of the total sample space, those 5 outcomes, right? Or you could use the and or rules. You could say, all right, the probability that something's greater than 3 or odd is equal to the probability that something's greater than 3 plus the probability that something's odd. But then you'd have to subtract off any overlap, any numbers that are both greater than 3 and also odd. Right? So how many of these cases are greater than 3? Well, 3 of them, 3 out of the 6 cases. How many of them are odd? 1, 3, and 5. That would be 3 out of 6. But are there any cases that are greater than 3 and also odd? 5. So you'd have to subtract that case off. You would end up getting 6 out of 6 minus 1 is 5 out of 6. So you can either kind of use a pictorial approach, right, to find this, or you can use a formula approach using the OR formula. Okay, so what I'm using here is the probability of A or B is the probability of A plus the probability of B minus the probability of A and B occurring at the same time. All right. So then let's do the same thing for the second part here, an even number or a 5. Okay, so let me scroll down a little bit. An even number or a 5. I'll switch to black here. Probability of an even number or a 5. Let me do it kind of formulaic. That would be equal to the probability that something's even plus the probability that it's a 5 minus the probability that it's even and a 5 at the same time. And the probability that the number is even is 3 out of the 6 rolls are even, 2, 4, and 6. The probability that it's a 5 is 1 out of the 6 cases. And the probability that this is even and 5, well, there's no way that a number can be even and 5 because 5 is not an even number. That's 0 out of 6. So this would be 4/6 or 2/3. Okay. All right, so that's that problem. Let's take a look at the next one. Number 7. So number 7 said, we have a Gallup poll here. Okay, so it's some people were asked, 1,005 people were asked, how likely were you to read Bill Clinton's autobiography, My Life? You can tell the age of this textbook, pretty old. The table shows how they were selected. If we select a person at random, so one person, what's the probability that the person responded will definitely not read it? Okay, not read it. Definitely not read it. Okay, well, that's a simple probability. So we're going to take the entire table, 1005, right? And then the event would be that they'll definitely not read it, which is this group, 382. And so that turns out to be, what is that? Well, I'll just leave it as a fraction. Might as well just leave it like that. I didn't bother to compute it, so we'll stop there. Okay, in part B, it says, what's the probability that a person will probably or definitely read it? Okay, so probably, or I'll use this symbol, definitely read it. Okay, so that's going to be the probability that someone probably reads it, plus the probability that somebody definitely reads it, minus the probability that they probably read it and definitely read it. Okay, well, the probability that they probably read it is 2 out of the, or sorry, 211 out of the 1005. Definitely read it would be the 90 here, right? And then we would have to subtract off any overlap between these. But there's no person that said both they will probably and definitely read it. So this is 0. And this illustrates a point, right? Whenever you're dealing with the whole sample space, all the individual elements in the sample space are by definition not overlapping any other ones, right? So that's why we were able to add up things before. In the first day, we actually just added up probabilities. And I just said, trust me why that's true. Now we know that OR is addition, as long as there's no overlap. But if you're looking at the sample space, you can freely add up individual things in the sample space because none of those overlap, right? So this would be a total of 200 and, what is that? 301 out of the 1005 cases. All right. Let's take a look at number 8 then. So number 8 says, if a single die is rolled one time, what's the probability of getting an odd number, or a number greater than 3, or an odd number, or a number greater than 3 and an odd number? All right, so again, I'm going to copy this to 2 because I want to be able to do both of these separately. Okay, let's take a look at number 8. If a single die is rolled one time, what's the probability of getting an odd number? Well, the probability of odd, well, let's list the sample space. 1, 2, 3, 4, 5, and 6. Everyone's equally likely. Odd numbers are 1, 3, and 5. So hopefully agree that that would be out of all 6 options, 3 of them. 3 out of 6 or 50%. Okay, a 3 or an odd number. That would be the probability of a 3 or an odd number, right? That's going to be equal to the probability of having a 3 plus the probability of having an odd number, because OR is addition, minus the probability of a number being 3 and odd at the same time, right? So the probability of 3 is 1 out of the 6 cases. Odd is 3 out of the 6 cases. But what's the chance that a number is both 3 and odd? Well, to be 3 and odd, well, 3 is odd, so that would be 1 out of the 6 cases. So we're back to 3 out of 6. Okay. Probability of 3 or odd. Greater than, oh, I messed up here. It's not the probability that it's 3, it's the probability that it's greater than 3. Greater than 3. Greater than 3 are these numbers here. So that's actually 3 out of 6. I'm just looking at my key and it didn't match. The probability we have an odd number is 3 out of 6, and the probability that we have both a number that's greater than 3 and odd. Well, greater than 3 and odd is one of the cases, so that's 1 out of 6. So actually this is 6 minus 1 is 5 out of 6. So sorry for the confusion there, 5 out of 6. The other way to do that would be to just consider the whole situation and like draw out the sample space and then go and individually include things in one. So we're talking about the entire sample space here, and then we could go back and include just numbers which are greater than 3 or odd. So all the numbers that are greater than 3 have to be included, or we need to include any odd numbers, so we would also include these, and then you could count those up, and that's a total of 5 out of 6. So you can either use a pictorial approach or you can use a formulaic approach. Okay, the last one says a number that's greater than 3 and an odd number. All right, so we haven't talked about the AND rule. Okay, so let's do this one just this pictorial way. We want the probability that something is greater than 3 and an odd number. So right now I don't have an AND rule defined, so I'm going to do that with a picture. 1, 2, 3, 4, 5, 6. We want to include all the numbers that are greater than 3. Okay. Oh, they have to be greater than 3 and odd. So I can't include it unless both these things are true, greater than 3 and odd. So these numbers are not greater than 3, so I can't include those. Okay, this number is greater than 3, but it's not also odd. This one is greater than 3 and odd, so I can include that one, but not this one. So actually, this would just be 1 out of 6, right? And our only way to do that at this point is to just do it with a picture like this. All right. And then the last problem that was in the part that we could do so far is this one about the homes. All right, so it says, in building a new home, a contractor finds that the probability of a home buyer selecting a 2-car garage is 70% and selecting a 1-car garage is 20%. That accounts for 90%. They don't build 3 or larger garages, so that means the rest of the people must have no garage. Maybe we should list out the possible sample spaces here. The outcomes are no garage, 2-car garage, or a 1-car garage. So maybe I just do it this way: no garage, 1-car garage, 2-car garage. And the probabilities associated with these are 2-car garage happens 70% of the time, 1-car garage 20% of the time. That's what's in the problem. So that's what's provided in the problem. Okay, part A asks me what's the probability that the buyer will select a 1-car garage or a 2-car garage. Okay, so that's going to be the probability of 1 car plus the probability of a 2-car garage, but minus the probability of a garage that's a 1-car and a 2-car garage at the same time. Well, we can't have both, so this probability is 0. These are mutually exclusive. You can't have a garage that's both 1-car and 2-car. So it's just going to be 0.2 plus 0.7, and so therefore it's 90%. There's a 90% chance that a buyer will select either a 1 or a 2-car garage. What's the probability that the buyer will select no garage? Well, because these things all have to add up to 100%, the 10% that's left over. Maybe I could write it like this. The probability of no garage is 1 minus the probability of 1 or 1-car or 2-car garage. So it would be 100% minus the 90%, which is 10%. And then for the last one, we want to find the probability that the buyer will not want a 2-car garage. Okay, so not a 2-car garage, or maybe I could write this way. The probability that they do not want a 2-car garage, not a 2-car garage. Okay, well, that's going to be everything that isn't that. So it's going to be 1 minus the probability of having a 2-car garage, right? So if the probability of having a 2-car garage is 70%, then that means the other 30% is the probability that they would not have a two-car garage or not want a two-car garage. All right. All right, I think we're going to stop there for the second part, and then we will go on to the AND case and develop the AND formula and its special case in the part